Hi, everyone. Welcome to Amir's last lecture. We'll give folks just a minute to join. Amir, do you want to describe a little bit about what we'll cover today and then jump into announcements?
Yeah, absolutely. While we're waiting. So, hi everyone. Welcome to my last lecture for for this year-long Qubit by Qubit series. So today we were going to be talking about near-term quantum algorithms. Specifically, we're interested in discussing what are some things that we think we can do. This was against an active area of research that we think we can do with quantum computers that we have available today and in the next 5 to 10 years prior to when we get fault tolerant quantum. So with that, yeah, maybe I will pass it along to Rachel for announcements.
Yep, I'll try to make that. We do have a few announcements with the end of the course coming and just some of the activities that we have to tend to accordingly. So first, everyone should have already received an email last week from our team regarding the survey that you have to complete to get your certificate for the course. So as you all know, this is a first of its kind effort to make really accessible and engaging quantum education widely available and available at scale. So we're really curious to hear about what you really enjoyed in the course, what you like about quantum computing, just your general attitudes toward the subject, and of course, opportunities where we can improve, hopefully for next year. So please complete that. It's due May 5th, so this coming Wednesday by midnight Eastern time. And again, it is required to get your certificate. So please check your inbox if you haven't seen that come through already, and you'll get several reminders if you don't complete it this week. So just get it done, or you'll get an email every single day asking you to get it done until you submit yours. Secondly, I talked about the technical assessment last week and we posted on Canvas about it, and you should have heard about it in your lab section. Unfortunately, we still heard from many students that they didn't get it completed, or they didn't know that they were supposed to complete it by a certain deadline. So please, of course, at this point you should know this, but please read the announcements on Canvas, especially in this last week. There's really important information coming out and deadlines that you have to adhere to. However, we are going to extend the deadline for the technical assessment also to May 5th. This one's at 1 p.m. Eastern. So if you haven't completed it and your deadline already passed, it will be reopened after the lecture. It's just a completion grade, like we've said before. And no matter what, no matter when you take it, you will only have a 60-minute block to complete it. So if you missed your deadline, please log on. May 5th is the absolute final deadline extension. If you miss it at that point, there won't be anything we can do about it. And then just two additional announcements. So we've had a bajillion questions about Canvas and YouTube and what will happen to course materials after the course concludes. I've mentioned it before, but we pay actively for Canvas for each student. So unfortunately, there's no ability for us to sustain the actual Canvas portal beyond the course. However, if you have certain materials that you want to refer back to, please download those. The YouTube links will continue to be available, so you can watch lectures again if you need to. The one very important caveat here is, as everyone knows, these are copyrighted materials. If we see them circulating among students outside of the course, we will remove them. So don't abuse the privilege. Feel free to save them for your own reference and your own learning, but that's it. And then just lastly, on a very happy and exciting note, we would love those of you who are attending today live, and for those of you who watch this as a recording later, next Sunday for our final lecture, we have a really fun day set up. So we'll have a guest lecture with members of the Qubit by Qubit Advisory Board, which include Scott Aronson, an award-winning, renowned quantum theorist, incredible faculty from UCLA, MIT, Amir and Fran's mentor, and lab So please do come, and we have guests from IBM joining and special surprises planned. So we can see how many students are attending on this side of the lecture. So we would love for them to see as many students who participated in this course join, have the opportunity to ask questions and engage in real time. So as always, next Sunday, May 9th, 2 to 4 p.m. Eastern, we would love to have as many of you here possible for a really, really fun celebration. And that's it for me. Amir, you can take it away.
Hey, thanks, Rachel. So with that, let's start our last lecture for the year-long Qubit by Qubit course. And again, the first slide of this lecture is going to be the quantum algorithms landscape. So as we discussed, there are different quantum algorithms. So we've talked about or introduced the Deutsch-Jozsa algorithm. We've briefly introduced Shor's algorithm. We've talked a little bit more in depth about Grover's search algorithm. And what the first three algorithms assume is that we have a perfect quantum computer, meaning that we have as many qubits as we want, and there are no errors present in our quantum circuit. However, and this is something that we saw during the past two lectures where we talked about quantum hardware, that is not the case for present-day quantum devices. So we need to think about what can we do with the quantum computers that we have available today or in the very near future. And that brings us to, of course, the topic of near-term algorithms that is highlighted here. And I think this lecture is important in the sense that it really teaches us how to think about programming a near-term quantum computer or a quantum computer that we have available today. So, you might have coded up some small instances of, for example, QKD, Grover's algorithm, or similar algorithms for your practice exercises or for your lab section. But the general problem is that the error that is present in the current day quantum computer gets out of hand for large quantum circuits. So for example, the largest number that's been factored using Shor's algorithm, I believe, is 35. And beyond that, there's just so much error in the system and they accumulate to the extent that you really can't do any proper quantum computing. So we really can't run any of the algorithms that we've discussed, at least in the class of the first three algorithms, without error correction for any meaningful instances. So that brings us to thinking about near-term algorithms, which take these restrictions into account for when we actually try to program a present-day quantum. Again, what do we need for running algorithms? In general, we need many qubits. In an ideal world, you want either no noise or error correction, so a way to compensate and fix those errors. And of course, the three elements that we've been talking about throughout the course, namely superposition, entanglement, and quantum interference. Specifically the properties that we're looking for, and again, these are laid out by the DiVincenzo criteria that we've discussed the past two lectures, but in like layman terms, we want enough qubits, and by enough, I mean as many really as we need to execute the quantum algorithms that we want for the instances. A way to fix errors if they occur, in case our system has errors, a set of gates that are universal, and the capability to read out the state of our quantum circuit at the end of the algorithm. Now, so what we want for quantum computing is, again, as I mentioned earlier, no errors, and that could be no noise, or error correction and perfect gates. We want no limitations on the number of qubits that our device has. So again, since we want to be able to run any instance of any algorithm that we want, and we want no limitations on the number of gates that we can execute. And sometimes the number of gates that we can execute is referred to as the depth of the circuit or circuit depth. And again, this goes back to having perfect gates. So that's this third condition that I have laid out here is essentially equivalent to having perfect gates. Well, but in reality, we don't have any of the above. In fact, we have quantum processors with limited number of qubits, somewhere between 50 to 200 in the course of the next couple of years. We don't have error correction yet, and that limits the depth of the circuits that we have. So that limits how many operations we can execute, how many gates we can implement before our circuit loses its fidelity properties or the coherence properties. And this regime is known as the noisy intermediate scale, NISC referred to by some, or simply near-term quantum devices. And this just goes to acknowledge that our system isn't perfect. The qubits are noisy, the gates aren't perfect. We don't have a lot of qubits, somewhere between 50 to 200, and of course, that's a quantum device instead of rather than a necessarily universal quantum computer. So the state-of-the-art quantum processors available today are superconducting quantum processors. That being said, we're not saying that superconducting quantum processors necessarily will be the technology of the future. We don't know that. But based on what's been demonstrated up to today, most notable quantum algorithms or quantum circuits or quantum computing results that have been demonstrated on large instances have been demonstrated on superconducting quantum processors. Of course, trapped ions are also another promising platforms that are well developed compared to the rest of the field of quantum technologies. The number of qubits is roughly between 50 to 100. Again, we don't know the numbers that the companies like Google and IBM aren't publishing necessarily, but we expect that the best devices today fall in that number, in that range of number of qubits. Our T1s and T2s are somewhere between 50 to 100 microseconds, so there is a time limit for how long we can run our circuit. And our 2-qubit gate fidelities are about 99.4%. So that really limits how many gates we can apply, how many 2-qubit gates we can apply before our circuit loses its accuracy and its fidelity. And there hasn't been a demonstration of a useful, and I want to emphasize useful here, quantum advantage instance. So of course, there was a quantum supremacy result from 2019, which basically showed that quantum computers are much better at sampling quantum circuits than classical computers are. But in terms of something that could actually have an application to any fields or any areas beyond just a quantum computing demonstration, that is yet to be seen. So with that, the question comes up then, what can we do with near-term quantum computers? Or rather, what do we think we can do with near-term quantum computers? Because this is an active area of research that's ongoing right now. So we think that one of the first applications of quantum computers, near-term quantum computers, is going to be quantum chemistry or simulating other quantum systems. So we can find the most stable configuration of a molecule. Now, what could that be used for? Well, the use cases would be, of course, for synthesizing medicine, coming up with more efficient and less costly fertilizers for farming and for again, food production industry, and of course for designing better material, which could be material for quantum computing, but in general could be material for any purpose. And another application that we anticipate is better optimizing complex problems. And the use cases for this would be in, for example, finance, when you're trying to find the most efficient and the most really profitable stock portfolios, or for scheduling. For example, if you're trying to schedule flights in and out of an airport, what's the most efficient way of doing that? Or even in machine learning. That being said, every one of these things that I'm pointing out to right now is an active area of research, and there's a lot of ongoing work happening. So overall, there hasn't been a meaningful demonstration for quantum advantage in any of these areas yet as of today, but we anticipate that we are going to see something within the next 5 to 10 years, which is very exciting. Now, so the idea here is that our quantum computers by themselves are not good enough because, again, we have limited number of qubits and limited number of operations that we can execute. But what if we combine the power of these quantum circuits that we have with the classical computers that we already have available to achieve quantum advantage? So we want to combine the small quantum computers that we have available with the classical computers that are sitting around and see if we can do anything meaningful with them. And the way that we like to describe this in qubit by qubit is using this quantum classical factory analogy. So let's see what happens in our quantum classical factory. So again, we have a quantum computer and a classical computer, or it could be multiple quantum computers and classical computers. And they kind of work like in the following way. So we first run a quantum circuit. And again, the first part of this quantum circuit will be initializing everything in an equal superposition, then running a quantum circuit using our quantum computer here. And then we measure the results of this quantum circuit. Now, we are going to see what this quantum circuit looks like in a moment. But before we get there, let's talk about the workflow. So how would the quantum computer and the classical computer work together? So far, again, we started with some state. We run a quantum circuit, which we're going to discuss, and then we measure the results. Now, we feed these results into a classical computer. And the classical computer does some set of operations and comes up with new parameters. And now the classical computer gives these new parameters that, in a way modify this quantum circuit to the quantum computer, and the process repeats. So then, after the classical computer sends instructions to back to our quantum computer, we will run another quantum circuit. And we repeat this process for some number of iterations, which depends on the problem and what we're trying to address, until we reach a solution. And then at that point, we just write down the solution and everything's all good. And one way of thinking about this is we're utilizing each of these resources, namely our quantum computer and our classical computer, in areas where their strengths lie. So quantum computers are good at running quantum circuits, so we're going to have them run quantum circuits. And classical computers, have a lot of memory. They basically have no error because we've reduced the errors and we have error correction for classical computers. So we can use them to, do calculations that are intensive and don't require a quantum computer. And then we can go back and forth between the two until we find a solution to a problem. Now that problem can be optimization, can be finding the most stable configuration of a molecule, or anything of that sort. And if you want to look at the workflow, this is what it looks like. So we start with an initial state. We have a quantum circuit that's, if you notice it, so the U is just a unitary operator, which describes the circuit that we have. But it involves two parameters, so it's parametrized. And hold that thought for a moment, we'll get to it. And then we measure the circuit. We feed the results of the measurement to our CPU, or classical processing unit, which is the classical computer here. And then the CPU will calculate what new parameters should we feed into our quantum computer. And then the process will repeat until we reach a solution. Okay, so let's talk about what would this quantum circuit look like? So the idea here is that we want to use a tunable quantum circuit. Now, this tunable quantum circuit is called a variational quantum circuit. Variational and tunable are the same thing. So we start with all states in zero. I just told you put everything in an equal superposition using Hadamard on each qubit. And then we apply a set of entangling gates between all the qubits that we have to create some entanglement in the system. And now we add single qubit operations, or in this case, I'm just showing them as U with some arbitrary unitary. We apply single qubit unitaries to each qubit in the circuit. And the amount that we apply each of these unitaries is described by this angle theta. Now, this thetas here, theta 1, theta 2, theta 3, all the way to theta n, are tunable parameters that we can change from iteration to iteration of the circuit. And in fact, going back to our analogy, this is these are the quantities, these are the tunable or variational parameters that the classical computer, computes or figures out what they should be and tells a quantum computer to, okay, now run your quantum circuit using these parameters, using these new variational parameters. And of course, we then repeat this for this entangling layer and the single qubit layer here. So what I'm boxing up here for the number of layers. So we do entangling single qubit, entangling single qubit, entangling single qubit. Now repeat this d times, or d is just a fixed number. And we end up with some state at the end of this computation, which depends on these tunable parameters. And finally, we measure the state of the qubit. And now we feed the result of this measurement to our quantum computer, to our classical computer from our quantum computer. Now, one way of thinking about this is that we have noisy qubits and gates. So we try to compensate for the fact that, again, there's noise in the system and that we can't have too many of these gates or qubits for that matter by adding tunable parameters that hopefully we can somehow learn through this repetitive process and find what the optimal parameters are by combining our classical computer with our quantum computer. And one way of thinking about it is that for each of these unitaries, these tunable unitaries, you essentially have a knob on your block sphere. And you can tell your system, your qubit, hey, I want you to turn, for example, by let's say pi radians around the x-axis, which gives you a full Pauli x gate. Or so maybe let me write this down. So I can do for example, u can be equal to rx of theta, and then I can have theta equal to pi, which gives me essentially u would be equal to the Pauli x gate. Or I can have theta is equal to pi over 2. So instead of rotating by pi radians around the x-axis, I can also ask the system or the qubit to turn by pi over 2 radians around the x-axis. And in that case, I get u is equal to e to the I pi over 4, and so on and so forth. So that's the degree of tunability that I'm talking about. Essentially, we can tell the system, rotate by this amount around a certain axis, and it will do it. And this angle, so the way that we figure out how much you have to rotate around each axis is by utilizing our classical computers. So this tunable circuit template, so this I guess unitary, like the format of this entanglement, the part that creates entanglement, the entanglement unitary and these single qubit operations. This is a template for the circuit, and it's called an Ansatz. Ansatz is a technical term, and it actually comes from German, and I think it means template. And now what we do is that we fill this template with our choice for tunable parameters. And again, these tunable parameters are things that that change essentially by through the quantum computer and the classical computer working in tandem. So again, let's take a look at how what is an example of that, how that works. We have the quantum computer, which I'm just writing as QPU in this case. The quantum computer runs the quantum circuit, and we end up with some final state. Let's say this psi of theta. So this final state depends on the tunable parameters that we're feeding into our quantum computer using our classical computer. And then we basically measure the circuit, and that gives us this E, which is the result of the measurement. And again, the result of our measurement also depends on these tunable parameters that we're feeding to our circuit, or these variational parameters that we're feeding into our circuit. And then we send the result of the measurement to a CPU, to our classical processing unit, or our classical computer. And then what the classical computer does is that it optimizes the value of this measurement outcome, this energy that we're looking, by essentially doing some classical process. And based on that, it tells us what should the new values for these variational angles be in order to actually, reach the optimal circuit that we want for the task that we're trying to. And it feeds back these variational parameters into our quantum computer. And this process repeats until we reach something that we perceive to be the right circuit for the job that we're doing. For example, if we're trying to optimize or find the most stable configuration for a molecule, until our quantum computer, the resulting state after running our quantum circuit resembles this most stable molecule, this quantum state of this most stable molecule configuration. Now, we can compare the circuit that I showed you, these tunable variational circuits, with what we've seen before, for example, the Grover search circuit. So in the circuit for Grover's algorithm, all the gates and all the operations were prefixed. So we exactly knew how much, for example, like what rotation around what axis exactly are we applying at every step of the operation. But now with these variational circuits, we can tune and change some of these parameters using, again, the input parameters that we have to the circuit. And that is the biggest difference between Grover's or Shor's or most of these, or most of these algorithms that assume error correction with the near-term variational algorithms that we're talking about right now. But if you look a little bit closer, you'll notice that the overall structure of the circuit is fairly similar. So, we start by putting everything in a superposition, and then we have, an operator that entangles the qubits, and that is analogous to the reversion around the mean operator for Grover. So the second operator that entangled things. And then we also have single qubit operations here, which are analogous to the oracle operator. And again, in Grover, we also repeated this process for O of square root of n times, if you remember, and being the total number of states that we're searching over. And here we're repeating the process for now, another parameter which we can tune. So for D layer, some number of repeats that we have control over. And again, if you look at this closely, you can see that what these variational quantum circuits are trying to do, in a sense, is that they're trying to imitate the amplitude amplification speed up that we get from Grover's algorithm. So with that, there are a few notes that I want to make about these quantum classical hybrid algorithms or variational algorithms. So these variational circuits are a heuristic approach that try to imitate amplitude amplification, or in general the techniques that we know from the famous quantum algorithms. And here heuristic means that we don't have a guaranteed runtime for them, but we think that, again, this is something that we think, and also we can demonstrate for some of them using numerics, that they actually do run faster than classical algorithms. Now, in contrast, for example, for Grover's algorithm, we can actually prove that Grover's is faster than classical search using math or the tools that we've shown. Whereas like with these variational circuits, it's very difficult to prove using math that they're actually faster. But there are techniques and there are benchmarks that we can show that some of them actually perform better. And next is that not every variational circuit is created equal. In fact, there's this notion of expressibility that tells us how many different quantum states can we produce with our ansatz, which is our template. Now, some ansatz, some of these templates are more powerful, meaning that you can generate a larger number of states with them. But the drawback is the chances that they might be harder to optimize to actually find the state that you're looking for. So the art of variational quantum classical algorithms is coming up with a good ansatz for your problem. So there's not a one size fits all ansatz or template that can solve every problem, but rather they're different templates that are good for solving different problems. And really the art, the trick is to look at the problem that you have and somehow try to come up with a good template for it that is easy, that basically makes the interface between your quantum and your classical computers easy and makes the back and forth easy, and you don't have to do it too many times. Now, there are two famous variational algorithms, which effectively are a recipe for the template that you use to solve the problems. The first one is the variational quantum eigensolver, or VQE, which is used for continuous systems, for example, chemistry simulations. And the other one is the quantum approximate optimization algorithm, or QAOA, which is used for combinatorial optimization. Now, we're going to talk about QAOA in more detail in this lecture, but VQE has more subtleties and it requires more of a background in either the physics or the quantum chemistry of the system for us to do a real deep dive during this lecture. That being said, VQ has had some recent breakthroughs, and by recent I mean over the past decade. So actually, the idea of VQE was introduced not that long ago, around maybe 8 years, 7 to 8 years ago. And this paper here is the first demonstration of a variational eigensolver, or VQE, on a photonic quantum processor. So this article is actually open to the public. It's on Nature Communication, and you can go and read it. So I would encourage you to at least try to look through it and see if it makes sense to you. Okay, let's see. And then a few years later, there was a demonstration of this of a hardware efficient VQE approach for small molecules and quantum magnets by the IBM team. People have looked at scalable quantum simulation, again, using VQE of molecular energy. So they were able to reproduce the molecular energy structure for some small molecules using VQE, which is a powerful tool because as your molecule gets larger, classical computers actually have a very hard time at finding the ground state or the most stable configuration of these molecules. And there's no theoretical results actually because the system's just too complicated to study theoretically. And that's where we think quantum computers will shine when it comes to VQE in 5 years. When we have devices that are large enough with error rates that are so small, the hope is that we can actually use them, utilize them to find the stable configuration for some of these larger molecules that you can't do with even supercomputers today. Now, there have been techniques demonstrated for mitigating the error, such that for error mitigation rather, such that you can run longer and larger VQE circuits. Again, this is by the IBM team. And finally, one of the most recent results is this Hartree-Fock simulation on the superconducting quantum processor by the Google team. Now, Hartree-Fock is one of these templates or ansatz that we're talking about for quantum chemistry. This was the largest simulation or largest simulation demonstration to date, where they simulated a molecule with 12 atoms, with 12 hydrogen atoms. And again, it's a step in the right direction where we want to be heading. Namely, that we can do something with our quantum computers that you can't do with classical computers, or that there's no theoretical solution. So with that, let's take a 10-minute break. I will answer some questions after the break, and then we will be talking about the quantum approximate optimization algorithm, or QAOA, in more detail. And right now the time's 12:36 Eastern time, so let's take a break till, 2:36 Eastern time. So let's take a break till 2:46 p.m. Okay, well, welcome back, everyone. So before we dive into the rest of the material and talk about QAOA, let's answer a few questions. Rachel, do you want to?
Yeah, Amir, let me clarify two quick announcements real quick, and then we'll jump right into questions. So, of you asking, we're not in Canvas access right away. You'll have it available through this week, but count on May 9th when the course ends, or a few days after that, that will wind down the course. And then thank you. You reminded me, shared the happy news, no homework this week beyond completing the technical assessment and the post-course survey. So no traditional assignment, but you'll cover more about near-term in lab this week. Okie doke. For questioner, students were asking, is this related to error?
Yeah, so this is related to error correction in the sense that it doesn't assume error correction. So we're assuming that we have noisy qubits and we can only execute so many operations before our quantum circuit's rendered useless. Whereas if you're assuming error correction, you assume that you can run as many operations as you want for as long as you want.
Awesome. And then the gate that you talked about that you called U.
I think Rachel cut out.
Okay, yeah, for a moment I was worried if it's me.
No,
Yeah,
I can ask the question. So
thank you.
On one of the slides, you had this gate that was that said U entangle. And I think some of the students were confused what that was for. Like, do we necessarily have to entangle these qubits? What's going on there?
Oh yeah, actually, I guess okay. So yeah, so you just said what the gate does, so I don't have to go all the way back. So yeah, the U entangle. We're assuming that U entangle is a set of gates, probably 2 qubit gates or more, that creates entanglement in the circuit. And now the reason why we want entanglement in the circuit is, well, first of all, to of course imitate the speed ups that we've seen with our other quantum algorithms, the ones that have a proven speed up. But also in general, entanglement is one of the 3 resources that we have at our disposal, right? So we have superposition, which we create at the very beginning stage of the circuit, then entanglement, and then we want to do quantum interference by essentially repeating this entanglement operation in our single qubit operations. And this U entangle, this entangling set of gates, depend a lot on the ansatz that you're using, and we're going to see it in action for QAOA coming up next as an example.
Okay, then a lot of students were suggesting that the whole process you described seemed very similar to machine learning. So is there a relation there, and is this also applied to quantum machine learning?
Yeah, so quantum machine learning is of course slightly different, but the idea is very similar. Because if you think about it, and for those of you who are familiar with machine learning, in machine learning you have, for example, neural nets with these tunable parameters that you're trying to train, such that your neural net is good at, for example, distinguishing handwritten letters or handwritten numbers, digits. Now, the process is similar here in the sense that you're also trying to train the parameters of your quantum circuit. Now, in this case, such that the final state is closely resembles or is the most stable, the state for the most stable configuration of a molecule, let's say, or the optimal flight schedule, for example. So it is very similar in that sense, and I mean it's really nice that some students have noticed that.
Cool. And then I think a few students were confused about how exactly to create an ansatz. So there was a question about, if I want to create an ansatz for some particular problem, how should I proceed? How do I find a framework that will work? And then another student asked, the choice of ansatz is not a patent or trivial. So can you comment on that?
Yeah, so I mean, creating an ansatz is the art of designing these variational algorithms. Now we are going to see what the ansatz looks like for addressing combinatorial optimization problems, or just let's say optimization problems, and that is for QAOA. But for VQE, for example, the ansatz is inspired by this Hartree-Fock unitary, which is again something from quantum chemistry. So we essentially took something well known from quantum chemistry, and we've parameterized it properly, and we use it to tackle these quantum chemistry problems on our quantum computer. And it is not trivial by any means, by the way. So, whoever pointed that out, you're completely right. Like, designing an ansatz is not a trivial task, but it requires some knowledge of the problem and figuring out exactly what operations will get you close to, whatever property of the problem that you want.
Cool. And then one final question about chemistry simulation. So a student had asked, why can't we just simulate these models on a classical computer?
Mhm. Yeah, that's a good question. So with every electron that you add to the system, um, you're adding essentially, four new parameters, give or take, four new parameters to the system. So, one electron, you need to keep track of four parameters. And then now two electrons, you have to keep track of, well, 4 to the power of 2 parameters. So, if you have n electrons, you have to keep track of 4 to the power of n different parameters. And again, this goes back to why is it difficult to simulate a quantum system using a classical computer, because of the superposition that you have and the way that your Hilbert space or the space of possible coefficients expand. You with every let's say qubit even that you add, the number of possible numbers that you have to keep track of doubles. So once you go past 40, 50 qubits, then all of a sudden you run out of memory on even the largest supercomputers. And then for problems with 100 qubits, or let's say 50 electrons, then yeah, tough luck. It's you have to come up with nice approximations, nice classical approximations, and even that's difficult.
All right, I think that was all the questions for now.
Okay, amazing. And again, we will have another opportunity for answering questions at the end of the second part of the lecture. So with that, let's talk a little bit about the quantum approximate optimization algorithm, or QAOA, which is a variational quantum algorithm used for combinatorial optimization. Now, what is combinatorial optimization? So, the name might sound scary and unfamiliar, but it's probably a problem that most of us have experienced at some point in our lives. So, for example, you go to a candy shop and you have a certain amount of money and you're trying to maximize the number of goodies that you can buy. So let's say you assign a different score internally to each of these goodies, based on how much you like them. And you want to see, how can you maximize this internal score that you have with the amount of money that you have. And of course, the trick is that you don't want the overall price to go above your budget, but you want the score to be as high as possible. So I want to see, what combination of items should you buy to maximize the score. So that's a combinatorial optimization. Well, that's what combinatorial optimization is, pretty much. Now, optimization, and I will refer to combinatorial optimization as optimization from now on, has many applications in industry and in the real world. One famous problem, optimization problem, is the traveling salesman problem, which is that given a list of cities and distances between each pair, what is the shortest possible route to visit each city exactly once and then return to the city of origin. Now, of course, well, this problem is significant in the sense that, for example, if you're trying to do shipping between multiple cities, you want to lower your costs as much as possible by traveling the shortest path between all the cities, but you also want to end up visiting every city such that you can actually drop your, drop the packages that you have for that city. So that is the traveling salesman problem. And again, it has applications when it comes to the airline industry, the shipping industry. What's another one that's good? The supply chain. That was a word that I'm looking for. For those of you who are familiar, for again, optimizing and making the supply chain of vaccine distribution more efficient, and so on and so forth. And of course, another problem that is big, and optimization plays a big role in, is the nurse scheduling problem, or in general the scheduling problem. So the nurse scheduling problem basically looks at how can we find an optimal way to assign nurses to shifts within a set of hard and soft constraints, such that basically accommodates everyone and no nurse has two shifts back to back. And so these are two famous problem instances of optimization in the real world and industry. Now, let's make this a little bit more mathematical in a way that we can actually try and tackle it using the algorithms that we have. So let's consider that we have n bits. So these are the variables that we're trying to optimize over. We're trying to find these optimal variables, and m clauses. And these clauses can be conditions that basically tell us different costs for different configurations of the problem. An example is if we have 3 bits, can be, and we show them as B1, B2, and B3, and 2 clauses. So, the clauses here can be, and again, the clauses are usually expressions based on these bits. So, for example, an example of a clause is 3 times B1 minus 2 times B2 plus B3. So, maybe let's look at this clause. So I have 3 times B1 minus 2 times B2 plus B3. And if, B1 is equal to 1, and again, these are binary, so they're bits, so they can either be 0 or 1. B2 is equal to 0, and let's say B3 is also equal to 1. Then this clause will give me 3 times 1 minus 2 times 0 plus 1, which gives me a value of 4. So essentially, you can put the value of each bit in every clause to get the cost of the clause, essentially. And here's another clause. So another example of a clause that I have is just B1 plus B2 plus B3. And what we're trying to accomplish here is that what are some values for B1, B2, and B3 that minimize the value of all these clauses? Could be minimized or maximized depending on the problem. Here we're sticking with minimized. Now, we can, using these clauses, this mathematical formulation that we have, we can write a cost function that tells us what the cost, what the total cost is for different values of the bits. And if you think about this, again, this is going back to the candy shop problem. This could be, like one component of it can be the total price of the candy that you buy, and another one can be the internal score that you have. And these go in the cost function. Now, we can define the cost function as the sum of our clauses, so just that simple. And again, going back to the example that we had when we had 3 bits, B1, B2, and B3, and 2 clauses that are defined, as follows. So this is, again, same as before. The cost function, which is going to be a function of the value of our bits, so the cost function of B1, B2, and B3, is just going to be the sum of these 2 clauses. So this is clause 1 here, and I have the second clause here. And when I add them up, I get 4 times B1 minus B2 plus 2 times B3. And this is my overall cost function. And this is something that then I can try and optimize. And actually, that is the goal of what we're talking about. Now, the goal is to find the value of our bits, B1, B2, B3, but of course, we can have many, many, many more that minimize, or of course, it could be also maximize the value of the cost function. Well, how can we do it? So one option is to try every single combination of zeros and ones. So if we have 3 bits, how many different combinations do we need to try? Well, so we have 3 bits, and bits are binary, so that's 2 to the 3. 2 to the 3 equals 8 combos. And of course, if you have n bits now that you're trying to optimize, that's 2 to the power of n. And the problem with that is that it grows exponentially with the number of bits. So that is not an ideal approach. In fact, it won't give us an answer. Now, for this problem, of course, there are many approximate algorithms, approximate classical algorithms that can guarantee that you get, somewhat close, or to close to a certain degree to the correct answer, but there's nothing definite. And now here we're trying to use QxQ as a heuristic quantum algorithm for tackling this combinatorial optimization problem. And of course, I'm not telling you that QxQ will solve this problem definitely, but what we speculate is that it has the potential for outperforming the best classical algorithms, again, in terms of potentially runtime or accuracy. So it might get us closer to the most optimal possible configuration. And again, going back to our quantum classical or classical quantum factory, we have our yellow minions, of course, which are the default minions, and we have these newly hired purple minions here. And the problem is that the purple minions and the yellow minions don't speak the same language. So just by default, they can't understand each other. Now, if they have a translating device, both teams could work together and the yellow minions could understand the language of the purple minions. So we're using this as an analogy for, of the analogy of these teams of minions for our classical bits and our quantum computer. So what we've talked about is that we have so far talked about a classical problem that exists in our classical world that depends on the values of bits. But now the question that I have, and I'm going to answer, is how can I translate the value of these classical bits to my qubits? Well, so we need to come up with a way to map the bit values to operations or operators such that we can apply them to qubits and understand the outcome, and to extract the outcome of the system based on different qubit configurations. Now, using this mapping, we can turn the classical cost function into a quantum Hamiltonian, which then the quantum computer can understand. So we started with the classical cost function, and we're trying to get to a quantum Hamiltonian, which is the language of our quantum computer. Okay, the mapping is actually fairly straightforward. So let's do the following. Let's map the value of a bit to an operator for a qubit using the following mapping. So here I have the bit B gets mapped to 1 divided by 2 times 1 minus the Pauli Z operator acting on that qubit. So if I have my bit, which I'm just going to show as B, is equal to 0, well, the corresponding qubit value is also going to be 0. So I'm going to have, so the corresponding qubit value is 0. And now the operator that I told you is this 1 minus sigma Z. And when I apply this operator to this qubit state, I want to get an outcome of 0, right? So, okay, let's try this. I have 1/2 1 minus Z, and this is just a Pauli Z operator acting on 0. Let's see what happens. So, okay, of course, this thing has 2 parts, right? So the first part, I get a 1/2. And then what happens when I apply a Pauli Z operator to 0? What value do I get? Well, so as a review, sigma Z applied to 0 will just give me 0, right? Or, I can write it as a +1 times 0. So I have 1/2 minus, again, minus Z/2. And when I apply Z to the 0 state, I get 1/2. So 1/2 minus 1/2 times the 0 state. And this gives me 1/2 minus 1/2 is just 0. So I get 0 times 0 state. And, this checks. So we wanted to get a value of 0 when we apply this operator to the quantum state 0, and that's what we end up with. Now, if I have my bit value is equal to 1, the corresponding qubit state is going to be the 1 state. And of course, there, let's try the same thing. So I have, again, 1/2 minus 1 minus Z applied to the 1 state now. And if you remember, if I apply the Z state or the Z operator to the 1 state, I get -1 times the 0 state. So here, what I end up with, I'm going to keep the 1/2 outside this sign. I have a 1 here that doesn't change anything. It's not an operator. And then I have a Z acting on a 1 state, and that gives me a -1. And I have a negative sign here, and negative times negative is positive. So I have this. So I have 1/2.
Ahmed, just to quickly
Yes.
clarify, when you say 1 minus z, you're treating the 1 as an identity matrix, right?
1 is an identity matrix, yeah. Or I mean, again, you can just think of it as a constant in this case, since you're thinking about Hamiltonians and operators.
Okay.
Thanks for bringing that up, actually. So, okay, I have, yeah, 1/2 times 2. So that just gives me a 1 times the 1 state. And again, this checks because I wanted to get a value of 1 when I apply the corresponding operator to the 1 state. So this way, I can go throughout my cost function and replace each of the bits, or each of the bits that I have in the cost function, with the corresponding qubit state, or with the corresponding qubit operator, sorry, for that state. Okay, let's see that in action now. And I want you to take, so maybe as I go along, so I want you to take a minute or two to think about these examples, and then we can go through them together. So yeah, so what would the Hamiltonian look like when I translate this cost function from the classical language to the quantum language? So what does the Hamiltonian look like?
Also, I mean, there might have been a typo on the previous slide. Some of the students are pointing it out.
Was there a typo in the?
So when you write z applied to 1, should that be -1, 1?
Oh, yes. Thank you so much. Yeah. Yes. Okay, so let's go through this together now. So I have 2 bits here, which means that I will need to map these 2 bits to 2 qubits. Okay, let's do it. So B1 here, the operator that it's going to get mapped to is 1/2. 1, and this could be identity or a fixed number, it doesn't make a difference in this case. And then I have a z operator applied to the first qubit, and then of course an identity to the second qubit, because we're only like the z operator is only for the qubit that corresponds to that bit in the cost function. And then B2 will get mapped to 1/2 times 1 plus, and in this case we're applying the z to, or the z operators for the second qubit. Okay, and what's happening here is that then we have B1 times B2. So this will get mapped to essentially multiplying the values that we have here. So I have 1/4 and then 1 plus zi, or think of it as z applied to the first qubit, z for the first qubit, and 1 plus, or okay, and these should be minus, by the way. 1 minus z applied to the second qubit. Okay, and again, the multiplication works the same way that just normal multiplication works. So I have, again, let me keep the 1/4 here outside. So I have 1 multiplied by 1, and then this 1 multiplied by this iz, or well, that's negative, minus iz. So iz, and then this zi times 1, so minus zi, again, z acting on the first one, nothing acting on the second one, and of course the last one is just minus zi times iz, which just gives you plus z. And let's try this. So maybe let's do, let's try to look at the case where B1, or let's apply this to the state 1, 1. So if we apply the Hamiltonian to state 1, 1, what do we get? So if B1 and B2 are both 1, we expect our cost function to be 1. Now let's try to verify that. So here I have 1/4, 1 minus, and let me just write this as, Z1, meaning that, Z to the first qubit, or Z2 QB1, and then Z2 and plus Z1, Z2 applied to 1, 1. Okay, let's start, filling in the blanks one by one. So I have 1/4 here. I have a -1 inside. Minus. Okay, so what happens in this case if I apply a Z to the first qubit? Well, the value of the first qubit is 1. So what I get is a -1. And I had a -Z, so that becomes +1. Now, what happens if I apply a Z to the second qubit? Well, same thing. The second qubit is a 1. So if I apply a Z operator to the second qubit, I end up with, again, -1. So +1, +1. And what happens if I apply a ZZ? So apply a Z operator to the first qubit, apply a Z operator to the second qubit, and then multiply what you get. So when I apply a Z operator to the first qubit, I get -1. When I apply a Z operator to the second qubit, I also get a -1. So if I just multiply the results, -1 times -1, I get +1. So I end up with another +1 here, times 1, 1. And what I end up with here is that I have 1 + 1 + 1 + 1, that's a 4. And then I have it divided by 4. So I end up with 1 times 1, 1. And this 1 here is the value, is what we expect from the cost function. And actually, I feel like there's a question.
Yeah, the students had a few questions here. So first, could you reiterate why we're using the expression 1/2 1 minus Z, like for any one of the bits?
Yeah, so that is the mapping that so if we go to the previous slide, right, that's the mapping that I showed that works. So if I apply that operator to that qubit state, I get the value that I expect, meaning that, if I apply the operator to the 0 state, I get a 0. And if I apply the operator to the 1 state, I get a 1. And that is what I want when I'm trying to map the value of a bit to the operators that correspond to the state of a qubit.
Okay. And then when we go on to the 2 qubit, the 2 bit case, I think a few of the students were confused about the ordering of the Z and the I. So why is B1 Z tensor I and why is B2 I tensor Z?
So what that means is that the Z tensor I means that we're applying a Z operator to the first qubit and nothing to the second qubit. And when we have IZ, it means that we're applying nothing to the first qubit and a Z operator to the second qubit.
I see. So when we write B1 as Z tensor I, it's like the first, so it's B2 to the right and then B1 to the left in both cases.
Exactly. And I mean, in fact, down the line, I kind of did the substitution where I just wrote down, I or ZI as Z1 and IZ as Z2. It's the same thing. And again, this is something that might take some time to get comfortable with the notion, the notation, but I feel like the concepts that are in the background should be, fairly clear.
Okay. And then a couple of the students were asking if it's possible to work this out for another case, like we did 1, 1, if we can do like 1, 0 or something.
Sure, absolutely. Why not? So let's do H of, you said 1, 0.
Yeah.
And maybe again, I want to take 30 seconds here and maybe try to do it on your own first, and then we'll go over it. And again, we're going to have another example in one slide, but take 30 seconds, do this by yourself, and then I'll go through it with you. Okay, so let's go through this together now. And again, I'm gonna expand the whole thing. So I'm gonna have, the form that we have up here, namely 1/4 1 minus z1 minus z2. And again, that's just a z operator acting on the first qubit, a z operator applied to the second qubit, plus z1, z2. And we're applying this to the 1-0 state. Okay, let's see what happens. Again, so nothing happens to the 1 when you act with a constant on a state. It's just an identity operator, so nothing happens. Now, what happens if I apply a z operator to the first qubit? Well, so in this case, the value of the first qubit is a 1. So what I end up getting for the outcome of my z operator is a -1. And I have a negative sign here, so when I multiply the two, I get +1. But now when I apply a z operator to the second qubit, the value for this z2 here, the value of the second qubit is a 0. So I end up with a +1 value for my eigenvalue. And there's a minus sign here, so I get a -1. And let's see, okay, so now I have the zz, right? So that is if I were to apply a z operator to the first one, take the result of that, the eigenvalue of that, apply z operator to the second qubit, and then multiply the eigenvalues. And here I have, so when I apply a z to the first qubit, it's a 1, so I get a -1 for my eigenvalue. And then when I apply the z2 to the second operator, that's a 0, so I get a +1 for my eigenvalue. So I have -1 times 1, which, this just gives me -1. And this is, of course, 1, 0. Now, if I, take the expression that I have in the parentheses and, multiply everything, add everything, do some arithmetics, I see that I get a 0 times the 1-0 state. So this is the value of the Hamiltonian. And again, if we look at this, so we had B1 times B2 for our cost function, and if either of those bit values are 0, the value of the cost function will be 0. So again, this 0 is also what we expect from C. Again, you can think of B1 times B2 as essentially an AND between the two bits. And the only way you get 1 is if both of them are 1. Yep. So let's look at another example now. Again, this is a little bit more complicated, but it's the same idea. So now we have B1 and B2, but now our cost function is B1 XORed with B2. Now, the trick here is that I can rewrite my cost function as B1 plus B2 minus 2B1 times B2. And let's check this. So B1 XORed with B2, again, bits, will give you a 1 if the values, if either B1 is 1 and the other one 0 or vice versa. And we get that here because if B1 or B2, if only one of them's one of them's 1, the other one's 0, then the first part here will give us a 1. And then the AND part, the second part where we multiply the two, we get a 0. And similar now, if both of them are 1, we expect to get a cost function value of 0. So we get, if both B1 and B2 are 1, we get a 1 for B1 here, a 1 for B2 here, which gives us a value of 2 for the first part. And then B1 times B2 will also be a 1. So minus 2 times that will cancel out the first part of the cost function that I wrote down, and we'll get a value of 0 for the cost function. So this mapping works. The point that I was trying to make is that this mapping works. And again, let's try to write down how our translation works from the bit values in the cost function to qubit operators. So we have B1 getting mapped to 1/2 1 minus Z1. And again, I know instead of Z1 here is equivalent to Z tensor product with I, which other one works easier for you. And B2 gets mapped to 1/2 1 minus Z2. And of course here, Z2 is equivalent to I tensor product with Z. So a Z operator acting on the second qubit and nothing happening to the first qubit. Okay, so let's take this out for a spin. So the Hamiltonian is going to be equal to 1/2 1 minus Z1, right? So that's for the value of B1. Now plus, again, 1/2 1 minus Z2. That's replacing the bit value for Z2. And now this is minus 2 times B1 times B2. So this is, and when I multiply these two, I get 2 divided by 4. The 2 comes from here, of course, and then I get 1 minus Z1 minus Z2 plus Z1 times Z2. So again, maybe again, take 20 seconds now that I've set this up and try to complete it. And after you're done, look at it and see if you can convince yourself that this actually does give you an XOR. Okay, so let's complete the steps together. So first of all, 2 divided by 4, the 2 divided by 4 that we have here is just 1/2, and that makes life easier. So let's see, I have, maybe I'll just, do it in 2 steps. I have 1/2 minus Z1 divided by 2, plus again, another 1/2 minus Z2 divided by 2. So that's just expanding the first part. The second part is again another actually it's going to be plus 1/2 because I have minus 1/2. Oh, sorry, no, that's going to be minus 1/2. My bad. So I have a minus half times 1, and then a minus 1/2 times minus Z1, which gives me plus Z1 divided by 2, and then I get another plus Z2 divided by 2. And again, a minus 1/2 times Z1 times Z2. So minus Z1, Z2 divided by 2. And things should cancel now. Let's see. So I have, a minus 1/2 here. I can cancel one of these plus 1/2. I have a minus Z1 divided by Z2 here. I can cancel that with the plus Z1 divided by Z2. And I have a minus Z2 divided by 2 with a plus Z2 divided by 2. And once the dust settles, what I end up with is 1/2 times, I'm going to factor a factor of 1/2, 1 minus Z1, Z2. So that's what the Hamiltonian looks like now. Okay, let's try applying this operator to different states. So let's try applying it to, let's say, the 1, 0 state, and then apply maybe to 1, 1. And take 30 seconds, try to do this on your own, and then we'll go through them together. Okay, so let's do these together now. So when we apply our cost function operator, which we've been referring to as a Hamiltonian because it can be a system Hamiltonian, it can give you, the energy or the cost of the system or of the these configuration of qubit states. When we act with this operator now that I have here on the 1, 0 state, I get, okay, I'm going to keep the 1/2. Nothing happens to the 1. And now I have a Z acting on the first one and a Z acting on the second one. So a Z acting on 1 and a Z acting on 0. Now a Z acting on 1 here gives me -1, and the Z operator acting on the second qubit, which is 0, gives me a +1. So now I have 1 minus, and everything in here, inside here, is just a -1. So I end up with just 1 times the state 1, 0. And this should, again, make sense because if B1 and B2 are different, meaning that if one of them is 1, the other one's 0, or vice versa, then we expect B1 XOR B2 to be 1. But now let's look at the scenario where both of the qubit values are 1. So I have 1/2 here times, again, the 1 stays. I'm just going to bring over the 1 over. And now I have Z1 and Z2, and they're both acting on a 1 state. So I end up with minus, and then Z1 acting on the first qubit, which has a value of 1, gives me an eigenvalue of -1. And Z2 acting on the second qubit, which again has a value of 1, has the state 1, gives me an eigenvalue of -1. So when I multiply the two, I get +1. And I have 1, therefore 1 minus 1, which gives me 0. And again, this value of 0 also makes sense because 1 XORed with 1 is 0. That's what we've seen earlier in the course. And again, this just goes to show that this approach, this mapping works, and we can faithfully map the values of the bits in the cost function to a set of operators that we call the Hamiltonian, using this 1 or 1/2 times 1 minus sigma z replacement for each bit, that each qubit will actually correspond to each bit properly. Okay, so now let's look at the QAOA circuit. What is the template?
Amir, could I ask a couple questions before?
Yes, please.
So just to clarify, all the math that we were doing earlier, that was just to translate the classical cost function into a circuit, into a Hamiltonian.
Yeah, and I mean, actually, if you think of it, most of the math was after we did the replacement and when we're just trying to simplify things. So, the biggest part, the part that is the mapping, is when we replace each of these B's with, the expressions that we have here. And the rest is just algebra to get it into a nice form. But there's no quantum mechanics there, or no quantum algorithms there. After we make the replacement initially, that's the extent of new things that we're doing. The rest is just algebra and simplification.
Okay, and then another question, kind of combining a few student questions. So are these mappings unique, or are there other ways to do these mappings also?
I believe these mappings are unique. At least in the bases for which we're looking for and for the problems that we're looking at, the problem that we're looking at. And actually, in when I to draw from my experience in lab, when I measure the state of the qubit, when the qubit's in state 0, I actually physically can measure a 0 using the proper tools and signal processing. And when the qubit's in the state 1, I can properly measure 1. And when I'm driving a transition in between, I can basically measure a value in between. And this mapping is analogous to actually what I measure in lab when I measure the state of the qubits.
Cool, thanks.
And that's where actually, I believe, if I'm not mistaken, again, the historical parts might not match as well, but for me as an experimentalist, that is the inspiration between this mapping between between a bit value to a qubit state using this operator. Okay, so with that, now let's see what the QAOA circuit looks like. So the first part of executing QAOA, of course, is to map the cost function into this Hamiltonian H. Of course, a property here that's important for us is the fact that this operator is Hermitian, which again, Hamiltonian is Hermitian, of course. And we'll see why that matters in a moment. So, of course, the next part is to start from the states being in all 0, all the qubits are in the state 0. Then we act with a Hadamard on each qubit, which puts us in equal superposition of all possibilities. And then we apply the entangling unitary of our template or ansatz. So in this case, the entangling, again, the graphics are a little off. The entangling unit has the form e to the power of I, this variational parameter. So this is our, let's call it tunable parameter, gamma. And then this H now here is the Hamiltonian that we talked about here, the cost Hamiltonian. And the reason why I emphasize that this operator needs to be Hermitian is because we want this e to the power of I gamma times H to be a unitary operation such that we can actually create the circuit for it. So this is the first part of the circuit. And this is, so in this case, in QAOA, we see that the entangling part of our ansatz is in a sense inspired by the cost function that we're trying to optimize. And I think that that's in a sense powerful. It's taking something about the problem and incorporating it actually to the circuit that we're trying to run. And the second part is the single qubit unitaries of the template or the ansatz. And in this case, the single qubit unitaries are just rotations around the x-axis by some angle beta. So again, beta here is another tunable parameter, and x is just a Pauli X operator, and we're rotating around the Pauli X operator in this case. And then we repeat each layer, each combination of entangling plus single qubit gates for p times, for p, or we call them p layers, which is again something else, another parameter that we can tweak. And then finally, we measure the state of the qubit, the state of the circuit. And then we send the result of these measurements to our classical computer. So the question that you might ask me now is, how do we make the entangling layer using our gates? So, let's, using the gates that we've seen. So mainly, let me tell you how we do it using, C naughts and rotations around the z-axis by some angle. Let's call the angle gamma actually for convenience. So okay, let's look at a Hamiltonian here, right? That has the form. I'm making this up as I go along, so this doesn't correspond to any particular problem, but this is an instance, an example of a Hamiltonian. So I could have z1 plus z2 plus z1 times z2. And again, z1 is a z operator applied to the first qubit, z2 is a z operator applied to the second qubit, and z1 times z2 is a z operator applied to each of the qubits. So then our U entangling, and again, this is a function of gamma, of course, will have the form e to the I gamma h. That's just what we saw in QAOA. And if I'm expanding h here, I'm going to have ei gamma, actually, okay, sorry, e to the power of I gamma here, and I will have times Z1 plus Z2 plus Z1 times Z2. Now, here's something that I have to emphasize that is a very nice property of the QAOA ansatz, and that is that all these Z's commute with each other. Since they're the same Pauli operator, the order in which you apply them doesn't matter. So, as a result of that, and only as a result of that, because if that wasn't the case, if these operators that I have in the exponent wouldn't commute, then I couldn't do what I'm going to do right now. But since they commute, I can essentially separate out the exponent. So I can write this as EI gamma Z1 times EI gamma Z2 times EI gamma Z1 Z2. So once we have that, once we have things in this form, which again, we can only write because all these Pauli's, like the order in which we apply sigma Z operators doesn't matter, then EI gamma Z1 is just going to be, as if I were to apply a rotation around the Z-axis by -2, and maybe let me erase that to make more space. So I have here times. So this is just a rotation around the Z-axis on qubit 1 by -2 gamma. And remember, like there's a factor of 2 conversion, there's a minus sign. And of course, nothing on the second qubit. And then, similarly, this EI gamma Z2 is as if I were to apply nothing on the first qubit, and then again, another rotation around the Z-axis by angle -2 gamma on the second qubit. So that stuff is easy. These are the operators that we've seen. These are just single qubit rotations on a block sphere. But now when we get to this EI gamma Z1, Z2, things get a little bit more interesting. And this is actually, what we have to deconstruct into using C naughts and RZs that we know. And in fact, I can make this operator using the following circuit. So I have 2 qubits. I start by applying a C naught between the first one and the second one. And then I apply a single qubit rotation around the Z-axis by, I believe, angle gamma on the second one. And then I apply another C naught from the top qubit acting on the bottom qubit. And this is equivalent to this operator that I have. So it's equivalent to e to the power of I gamma Z1, Z2. So using this mapping, I was able to deconstruct this unitary operation here that we hadn't seen before to the circuit elements that we've seen and we're comfortable with at this point, and our quantum computer is comfortable with, namely C naughts and rotations around the Z-axis by some angle. Now, of course, we can choose different 2 qubit gates, and that's going to change the construction slightly. Like, for example, you can use instead of a controlled NOT, you can use a controlled Z gate, and that'll change what the operators look like exactly. But I think overall, since we're used to using C naughts and rotations around the Z-axis, this is what the constructions look like. And of course, this was the extent of the math that we're going to see here. There's more to be explored, and I have the references listed towards the end of the slides. But overall, the point here was that we're trying to accomplish a circuit that looks like this. and we saw how we can deconstruct the entangling layer to quantum gates, single and 2-qubit operations that we're comfortable with and we've seen so far. And of course, the single qubit layer is just rotations around the x-axis of the block sphere, which we've seen. So yeah, this is an example of what an ansatz looks like for QAOA. Now, VQE ansatz are a little bit more complicated in my opinion, but each ansatz will depend on the problem that you're trying to solve. In the case of QAOA, it gives us a recipe to create an ansatz based on the cost function that we're trying to optimize, and the cost function goes into effect in this exponent. And it's going to change, what 2-qubit single and 2-qubit configurations that we use for creating this entangling layer. Now, the workflow. So the idea here is that we want. Yes, Akshay.
Could I ask a couple more questions, Amar?
Yeah, hit me.
So on the previous slide, could you talk about? I think a few students were confused still about where did the e to the I gamma h come from?
That's what
how did we go from h to e to the I gamma h?
Well, so e to the I gamma h is a unitary operation, right? Because h is a Hamiltonian or Hermitian operator. So therefore, I can actually execute this unitary operation on my quantum computer. And, I just went through how I go from, this e to the IH unitary that I told you about to, to the C naughts and rotations around the Z axis that we've seen so far.
Okay, and then when we have e to the I gamma Z1, how do we go from there to RZ minus 2 gamma? A lot of the students were thrown off by that factor of minus 2.
Yeah, so I guess this kind of goes back to our like one of the lectures that we had earlier in this semester, that if you're rotating around the RZ, around the Pauli Z axis, or on the Z axis of the block sphere by some angle theta, that is equal to EI theta divided by 2, in fact minus e to the power of minus I theta divided by 2 times sigma Z, right? So now, working back from the right side to left, if here I have I gamma times Z, then what is my theta in this case? Well, you can solve backwards and you'll see that the theta here is minus 2 gamma. So that's where that minus 2 gamma comes from. But again, I think that the biggest point of intuition that we should try to get out of this is that it's a rotation at the end of the day around the Z-axis.
Cool, thanks.
Yeah. If there are no other questions, let's just let's wrap QAOA up by talking about the workflow of the algorithm. So the goal is that we're trying to find the optimal parameters that maximize that, or in this case, minimizes or maximizes the expectation value of the cost function. Because again, we're trying to look for either a minimum in this case, but also could be a maximum value for a cost function. And we start by putting all the qubits in an equal superposition. Then we apply our quantum circuit, which has these tunable parameters gamma and beta for some number of layers. And then after we execute the circuit, we measure the results, the outcome of the circuit. And then we feed these measurement results into our classical computer or a classical processing unit, also known as CPU. And then our CPU does some optimization in the background, some calculation in the background, and comes up with these new variational parameters, gamma and beta, and then tells the quantum circuit or the quantum computer to run a quantum circuit with these parameters, gamma and beta. And we repeat this process until we're convinced that we're at essentially the minimum that we're looking for using our circuit. And then at that point, our algorithm returns a solution, tells us that, okay, with the number of layers that I had and this ansatz that I had, this is, the solution that I found, the lowest cost, or, highest cost, depending on what you're looking for, but the lowest cost solution that I could come up with is this. And then, it returns the solution in terms of like that's a bit values to the user. Now, QAOA is also an active area of research. The algorithm was actually first introduced in only 2014. So less than a decade ago, like 7 years ago at this point. And that's actually when I started college, like as a freshman, as a first year student. So it's a very new algorithm. And again, there's a lot of research that's happening. So there was a proof that showed that quantum approximation optimization is computationally universal, meaning that it could probably hit any like the minimum that you want if you run it for long enough. Now there was a demonstration of this QAOA on some graph problems using superconducting qubits, and of course there was another demonstration of QAOA for performing quantum factoring using this variational approach by mapping the factoring problem into an optimization problem. And it looked at essentially what are the shortcomings and what are the biggest error modes for running QAOA on near-term superconducting devices. So with that being said, looking forward, if you want to learn more about these variational algorithms, I would recommend looking at the original QAOA paper, which is the one that I had a picture of on the previous slide, and I have the link here. Now, there's a nice chapter on QAOA in the Qiskit textbook. And of course, the first VQE demonstration, which I talked about before the break, is also another, good result to look at. And also in general, the Qiskit textbook also has a chapter on VQE. And you might ask, okay, so what is next? So after you've done a year-long course in intro quantum computing, what can you be looking forward to? So in my opinion, I think these variational quantum circuits are very promising for folks who want to explore quantum computing now, because they can be executed on or ran on near-term quantum computers and quantum devices that, for example, IBM has available on the cloud. And now you can try to use your knowledge to design and execute your own variational circuit. So again, as I mentioned, a large part of the art of variational quantum computing or near-term quantum computing is coming up with ansatz that are good for the problems that you're trying to solve, that can actually reach that minimum cost function value that you're trying to optimize for. And I mean, a good part of that comes through experimentation, actually simulating the behavior of different ansatz and seeing how hard it is to optimize, for example, in your ansatz to actually reach that minimum value that you're looking for. And you could combine these quantum resources that you've learned about with the classical approaches that you have to solving problems, and see if you can maybe offload some parts of your problems that are hard for your classical computers onto your quantum computers and gain an advantage that way. And of course, everything that we've talked about here, especially in this lecture, is happening, the research is happening right now. So there are a lot of the questions that you might have, there might not be no answers to yet. And you could be the person that comes up with an answer to that question. So I would just like to encourage you to, again, experiment with your ideas, and the tools are out there now. You're a part of a lucky generation of quantum learners who have access to actual quantum devices and good quantum simulators. So you can try to experiment with your ideas and see if they work. And that is amazing. That's basically what I get to do as a PhD student now. You can do that right now as a high school student. So before I wrap up my lecture, I want to give a special thanks to the all-star team that I've had helping me with all these slides. So if you've noticed the slides that at least I've shown you, have some very nice graphics, some very nice ideas, and simplifying concepts from again cutting edge research to something that's more understandable. And that's all thanks to the team that I've had helping me. So I want to thank Katie, Sarah, and of course Rachel and Kira, who we've been meeting regularly, on a weekly basis about how to improve our presentation and teaching the teaching material. And on a final note, since this is the last lecture that I'm teaching, I want to welcome you to a quantum journey. Now you have the tools to first of all decide if quantum computing is something that's right for you, if this is something that you're interested in. And for those of you who are interested, again, I'm very happy that like nothing would make me more happy than to see students that are interested in what I'm passionate about. And I would like to encourage you to use all the resources that are available to you. For example, there's a QxQ textbook which is accessible online. You can now run circuits on quantum computers for free, which is something that I didn't have back when I was learning quantum computing. And there's so many resources available online that you can go and really take the next step in your journey. Prior to going to an institute of higher learning or a PhD program or a job. So definitely take advantage of that. Again, it's been great teaching this course. It's definitely been a challenge for me as well. I've never done anything on this scale. And I've personally learned a lot, and I hope you have as well. And with that, I would like to wrap up the lecture, and I'd be happy to answer more questions. Thanks, everyone.
Okay, let's see. I don't think there's any like large questions which a lot of people had asked. I think some people had some issues with the specifics of the math, and I think maybe like the larger message here is not so much the details of the exact math, but the idea that you can convert these classical cost functions into like a quantum circuit, right, Amir?
That I think that's the main takeaway message. I sent that my video's acting up right now a bit. I think
some of the students are saying that you went into a superposition.
Okay, I think I'm back. Yeah, I noticed this before in the pre-lecture check that we do, so I knew exactly what to do. But yeah, so I think the larger point that I want to emphasize, and again, we've tried to emphasize this throughout the course, is that you will get more comfortable with the math as you go along, and that is the personal experience that I can say I've had. But what is important to get out is the thought process and the conversion process that we've had. So we had a classical classical cost function, and we had to find a way for that classical cost function to be understandable by a quantum computer. So we went ahead and mapped, essentially replaced every bit with an operator that corresponds to the value of that bit. Now, of course, there was a bit of a math there, and again, it might not make sense immediately. If you look at it more, I think it will. But the main point is not the math, but rather the step-by-step process that we had. And of course, then we use that the expression that we get using this conversion as an inspiration for the ansatz that we use for our variational algorithm. And again, that is the point. So these ansatz are inspirational in a sense, meaning that they're usually inspired by some physics or some math in the background. And what we were trying to show you here is what is the source, like how do we come up with the format of this ansatz for a specific problem. And in this case, of course, that problem is combinatorial optimization. And then we want to see like exactly how does that form, or how can we map that form into the circuit elements that we're used to seeing, namely C naughts and single qubit rotations.
And could you talk about if VQE and QAOA, as they're currently being used, do they provide like an advantage over classical optimization algorithms, or will that happen in some time?
Yeah, so that's actually interesting. So VQ is a bit of a different monster, but let's talk about QAOA. So initially in the first, I wouldn't say like 4 or 5 years, like QAOA was introduced. There was actually a demonstration of QAOA, not on actual hardware, but rather a theoretical demonstration, not a theoretical, a numerical demonstration that basically showed that QAOA can outperform the best known classical algorithm at the time for a specific optimization problem. But then all the classical computer scientists got together and came up with even a better algorithm that beat QAOA's performance. So in a sense, it's going to be a little bit of back and forth, but that in and of itself will be good for computing in general, because if we can come up with better classical algorithms as a result of now having access to this extra tool, that inspires us to push our the quality of our classical algorithms more. That is valuable also. Now, VQE, once we get to larger and larger molecules, I think that is something that could be convincing. That we can argue, hey, this would be actually hard to do on a classical computer for the intuitive reasons that we have. So again, this is an active area of research, and probably a lot of the problems that actually you might be seeing in the Q&A chat, the answer that I'm going to give you is that we don't know yet, but you could be the person's asking that question can be the person who finds the answer. And I think that is the fascinating thing about talking about near-term algorithms, especially this lecture that we've had, that a lot of your questions are don't have an answer, and you could be the person who finds the answer for them.
Hey, Amir. Oh, Akshay, is there another question?
No.
Okay. I wanted to ask, one student asked kind of what was your journey into quantum computing, and I'm not sure that we've ever heard that. And so maybe if you want to end a little bit more with your own personal story, personal research, and we can wrap up after that.
Yeah, sure. So, I'm one of the fortunate few of at least, my generation of quantum learners that got exposed to quantum computing early on. So, prior to starting college, I knew I was interested in physics. I had a decent background in physics, and I wanted to major in physics in undergrad in college. But my advisor, my academic advisor, freshman year was actually one of the founding figures of quantum computing. One of the figures who was very well respected and active in the field. And I got exposed to quantum computing early on. And what I learned was that I really enjoy a lot of these concepts. Again, I might have not had understood everything off the bat. And in fact, this lecture that I gave you, I actually didn't learn these stuff till I started grad school a few years ago. That's how new this material is. But I realized that I enjoy quantum computing, and I found it to be very promising and something that's going to shape the future. So then in university, I was a part of different research projects. I did some research. I took courses that my university offered, and of course, I started teaching one my third year, my junior year. And that's a little bit, that's where things will be different for you guys, in the sense that now there's so many resources available online, and that you can access really at no cost, that you could learn about these things without taking a course at a university. Essentially, the world is your oyster, and you can access a quantum computer, and in fact even operate a quantum computer at the hardware level without needing to be in a PhD lab like I am, without being a grad student, and that is amazing. And I was always interested in the experimental side of things. I'm interested in actually running quantum algorithms and seeing these quantum effects on real hardware. So that's what I was doing in undergrad, and then for my PhD, I continued working in quantum computing, and I switched from these defect centers and solids that Eric talked about last week to superconducting qubits, which is what I primarily work on now. And yeah, I mean that's pretty much it. Of course, that's not the experience for a lot of the people. Like most, you guys are first of all very ahead in the sense that you already at least have been exposed to quantum computing and you know what quantum computing is. Some of you might know that you're interested in it, but a lot of the folks that are my age, and again, I'm not that much older than you, which just tells you, how significantly things have been, how fast things have been progressing since, didn't realize that they want to do quantum computing until third or fourth year of university or college. So yeah, I think you guys have a head start compared to me and folks that are 4 or 5 years older than you, and it's just amazing the things that you can do now compared to what the state of the field was even 5 years ago.
On that note, let's wrap up, and just a final reminder that this was Amir's last lecture, but we will all still meet again next week for a really exciting celebratory final lecture with members of our advisory board and folks from IBM. So we look forward to seeing you same time next week.
And congrats everyone. It was a hell of a year.